Thank you for this opportunity, and it's a good time for wrap up what have been changed for after more than 1 year, and this is the case that we there are so many things happen caused by after this earthquake, and it's cascaded, and there are so many things that we can see. And so I split my talk into two parts. First is things about cascading impacts, and the second part is about my research, which is tsunami. So there are also some research going on related to tsunami as well. So this earthquake is happened in the Sea of Japan, so the west side of Japan, which is this side. Many of you might know about 2011 tsunami, which is on the Pacific side, the other side here. Sorry for on site people, we cannot you cannot see the head of the title of this slide, but this is the situation. I mean, after 2011, Japanese government reevaluate the earthquake and tsunami all over the countries, and this side of Japan also one of the target. And this is what they did in 2014. Sorry, I cannot see, but this is what they did in 2014. So they reevaluate tsunami from new earthquake source. And actually, this side of Japan is not, actually they are also famous, not so famous compared to the Pacific side, but actually there are many tsunamis as well, like the famous one in 1993 and 1983 here. And the government has assumed many possible active faults, as you can see, like F number, something like that. So, and this event in 2024 was happened here in Noto Peninsula. Actually, yeah, we have the pre-event in 2007 as well. And actually, yes, and we actually already assume or concern about the possibility of earthquake at the fault line F43 and F42. So again, in the same report in 2014, so the government has already made some assessment, and the newly built hazard map has been already provided to local people, and they use these maps for evacuation drills and etc. for the planning. So they do quite well soon after 2011 and before this earthquake. But before that, so this earthquake in 2024 happens in, as I mentioned here, in Noto Peninsula, and which belong to Ishikawa Prefecture. And this earthquake is actually, I think I should go to this one first. The epicenter was here, and in Japan we have the intensity up to 7. So in some area it reached the top scale of the Japanese scale, and most of the area in Noto Peninsula reached like up to 2nd or the 3rd one scale. So the ground shaking was very strong. And I will come back to the curve later, but actually Ishikawa Prefecture is ranked one of the worst, less built earthquake resistant housing in the country. You can see that, for example, in the area that experienced 2011 tsunami, like in Iwate or in Miyagi, or here the Hyogo Prefecture or Kobe, the location where they experienced Kobe earthquake in 1995, or the area with green or dark green has very high level of awareness of earthquake resistant buildings. But unfortunately, Ishikawa Prefecture is one of the area that they have less building resistant. So that reflects why this time there were many housing damage caused by the earthquake. If you can see from this vertical curve for the earthquake, and the vertical axis show the damage probability, and the horizontal axis show the intensity. Sorry, in Japanese, but maybe you can guess. This is 5 plus 6 minus 6 plus and then 7 like that. So you can see, and these groups, these 3 lines are the building built with the old building, old codes. So you can see like here, most of the building were experience like intensity about 6. So compared to the new code, which is these lines, so the building is very weak. So what like Susana and Yona have seen in the field is actually what we have seen also from the data in the past. And this is also the photo from the field that we just visited last week. And still many buildings still right like that, and some of them they already clean, but still we can have a chance to see the remains. And this area is actually very famous for the local roof tile like this. So they use the local soil and they make a ceramic tile like this, which is heavy, and you can see the house is quite old. And this sign right here just show like this is like a preserved area for the cultural ways of building. So that's also reflect this kind of thing as well. And besides the damage caused by the earthquake, there are several damage caused by cascading damage caused by, followed by the earthquake. And for example, there are lots of landslide in the peninsula. There are quite big uplift to 3 or 4 meters along this side. And there were liquefaction in various area up to here and up to there out of the map. And also fires in several places. And also tsunami, of course, caused by the earthquake, but also caused by the submarine landslide in a bay, which I will speak a little bit more in the part 2 related to my tsunami research. So these are some photo example of the right after the earthquake. I took it from the prefectural homepage. So you can see that, as I mentioned, it's very cascade liquefaction in the area that right behind the sand dune. We have a big fire in the fish market that I will speak a little bit more, that also related to a very complex situation. Landslides in many area, and this disrupt the roads and etc. And of course tsunami, although limited, but also kind of some damage to the fishing port and the coastal defense. If we make that to the graph diagram like this, you can see that earthquake generate different types of cascade impacts and hazard that also generate other types of damage. But from my perspective, this time the damage to roads or other logistics related or transportation damage is very important and very famous, well known, significant for this earthquake. I will explain you a little bit. So I would like to go through each disaster briefly. So for example, landslide, this map from the government agency, GSI, Japan's geospatial agency, shows the red area, the landslide or other geotechnical failure in the whole peninsula. For those who came to Noto Peninsula with me last week, I think you have seen several of cracks on the road or shut down of the things like that. So this actually we yeah, it's quite very obvious in this area. And also another problem is like when the landslide stop the river, and it caused some sediments problem as well, and also the water in the river increase, and that is cause another like risk of flood, something like that. This is another problem. And things what they did in 2011, back into 14 years ago, how they recover the road at that time. What they do, they start, because the road along the coast were totally damaged. So they start what they call like comb, comb, right? There are many teeth. So they say like, okay, let's rebuild or recover the main, like a fishbone, right? The main rod first, and then they start from the teeth of the comb like that, or fishbone, and then through the road through along the coast. This is how they fix the road. You can read more in detail from this. And the same idea has been also made to this earthquake as well. For you guys, if you might remember, we start our journey from Toyama, and then we go through here. And as you can see, after earthquake, there was no connection from inland to the coast. Sorry, this is the sea. So they start building things like this, little by little, and they make like a big roundabout. So I check my GPS, and then we follow this kind of thing. And to go through this among this peninsula is quite difficult, because it looks close, but the road network is not that good, still not that good, because of this kind of construction work. So this this delay the construction recovery. And also I will tell you a little bit more how this related to the death as well. And from what I can read from the news, they also mentioned that they have no not good plan for the like how to secure this kind of heavy machine, or how to secure the manpower for this kind of road recovery, especially in peninsular types of topography that is can be easily to be isolated. So this is another thing that we have to improve. And for this slide, I took it from those published by the media. And you can see that most of the people were killed by earthquake, 86%. This is from the prefectural website. They expose this data by receiving the consent from the family. And yeah, and if we split, also also there was a tsunami, but I'll speak you a little bit more. But for tsunami, not so many people died by tsunami. Even tsunami could arrive at this time. Tsunami arrived in a few minutes, but I will speak a little bit more. But yeah, most people were killed by earthquake because that I mentioned, that the old house or the house is very weak to the earthquake intensity. And another thing is that the cause of the death. This is I took its data from NSK. They interview the police department, and they mentioned that like 14 of the people died because of the hypothermia, or very too cold situation, which is compared to 2011 tsunami. Most people died because of water, the drowning, but this time the hypothermia also quite big percentage if we convert to percentage. From what I learned from news or other reports, they mentioned that because of the road damage, even people could survive under the rubbish, but they have to wait for a long time until the rescue team could come and rescue them. So that is for us, we are quite surprised of this kind of number as well. So this is another thing that we should improve for the future. And also that is another the point that it's not necessary that most people will die because of the direct death or death caused by the building collapse or tsunami or landslide. But after a while, people have a bad condition of living or stress, depression, like that. So this is the data I took from the newspaper, like from 1995 Kobe or other events like here. And this is a number of the direct death and disaster related death. So I mean, they die after the event. So you can see that these numbers are not small. And actually, if you check compare with the Noto Peninsula earthquake, where this graph, about 200 people, 227 people died because of the direct death from many causes. But now maybe Professor Ego can mention later. But yeah, from the news, even at that time, the number of people dead by the other, I mean, after the earthquakes already higher than the people dead caused by the direct impact. So this is another thing related to medical issue that, or how we can prevent this kind of situation. As you can see, even the number here is not that much, but now the related deaths already go higher than other things. Another famous story is like after Kumamoto earthquake, people, you know, like staying in the school gymnasium or other public space, they have less privacy. So people, some people start to evacuate, staying, sleeping in their car, which is not a good condition of you know, like to rest or to live after disaster. So that is another issue, that how we can make sure the privacy of people in the shelter, and or how if people evacuate in the car or other area, how we can maintain their health. Liquefaction, as I mentioned, actually they also found liquefaction in wide range, even though the epicenter was here, but even far here in Niigata Prefecture, they also reported, and several places in Toyama or other area. In the field, we went to this area where we have sand dune in front, and yeah, we, of course, this is after 1 year, but this may be one of the evidence of liquefaction, that the manhole go up high like that. And yeah, so I took it, this one from newspaper. So this is the sea, and this is the area here where they have a Japan Sea, and we have the sand dune, and this is the underground water, groundwater, and then so table, and so it used to be sand dune, and they built some residential area in this area, and because of the earthquake, and because of the groundwater level as well, so the badly liquefaction has a report, and they found it in this area. This is from the report or interview by the expert in Japan. So I just take it from that. And for fire as well, of course, fire is kind of common things after earthquake, but for this event, I would like to give some example that is very cascade, and maybe we need to think about that. Of course, earthquake happened, but actually this area got like 2 to 3 or maximum 4 meters of uplift. So the earthquake didn't only damage the water pipes, but you know, like because of uplift, so it's more harder to get water from river because the land is up. And also they got the tsunami warning, so the local firefighter cannot stop the fire, of course, because they have to evacuate as well. So this is very complex situation. And so like this here, they say, so they have to wait until the government cancel the tsunami warning, so that, and but the land already lift up, so it's quite hard for them to take water from the river. So they from the news, they say they took water, seawater, to stop the fire after a day, the second day, the 2nd of January. So this is the thing that we have never think about that when we do the planning. And this is just to show you how it looks like now. They already remove everything as clean up as a ground zero. And this is another point that some of you who check the news in Japan, that's actually the earthquake was in January, the new year. But in September, there was a big flood as well in that area. So actually, after January, people start to evacuate, live in the shelter, move one time. Some person have to move 2 times or 3 times, and they. Oh, sorry, I have to move here. So of course, this is like peninsular and mountain area, so it's not easy to find a flat land or very safe land for building the temporary houses. But so they decide some area to build as a temporary house, but due to the big storm in September, some of the temporary house were the flood by that. That is another point that should be mentioned, that how to select the area for building temporary house. And of course, we have hazard map, but yeah, sometimes it's quite difficult to make decision for the limited area and source. This one about the uplift, as you can see, this area got uplift about 2 meters, and this area 4 meter. I think we were around here, and as you can see, this is like the pier, the fishing port, and this is the photo before and after from Google Earth. Oh, sorry, from GSI, the Ministry of Land Transportation. You can see that the whole port is up like that, or like this. So again, I mean, no, we have never think about that when we make a plan for tsunami or things. Of course, this area was lucky for tsunami for uplift, but the recovery of fishing port is another problem. How we can do that? And yeah, this is from some photos that we took from the site. Is how it looks like if we stand in around the road and we took the photo, look it down to the sea. You can see more here. It used to be under the water, and this one I took it from a newspaper here. Kind of possibility of how they can rebuild the port, the uplift port. So first one is like we excavate only in the green area so that we allow boat to go through in the deeper part, or they just build a new pier just to connect here to the one, or make a slope here, or just forget about this one and build a new port like that. So, but I mean, what we discussed in the field, that my own feeling is that it's not so big fishing community compared to like 2011. So after 2011, we rebuilt the subsided port like that, but and there are still many fishing community, but this time and in this location maybe not that much, and yeah, and the damage is quite large. So yeah, still under discussion what is the best way to rebuild. And yeah, I would like to show one example of 2011, how they make a good new building of recovery of the port and the other seashore facility. This area is like after 2011 tsunami, they have to increase the size of the seawall, but having higher seawall means we have to have bigger or wider of the seawall, right? So that's might consume more space and reach to the sandy beach, which is quite beautiful in summer. So of course, this kind of plan got objection. Local people doesn't like this plan. So from several well, I mean, workshop or exchange of idea or negotiation. So they came up with the result of like, okay, the government resume the previous extension of the wall. So we will not go through the sandy area, but we increase the land elevation behind the seawall, like this part. So we top up like this, make a road and like shops and other things, and we ask people to move here. So it's like when you drive on the seawall like that, or you have a shop on the seawall. That can save many problem, right? Can solve many problem. We can have a high seawall. We can save the beautiful scenery, and we can save the space for the nice sandy beach. So this is one good example in my opinion that we did in 2011. But yeah, But this kind of idea cannot be just copy and paste to 2024 and Noto Peninsula, because this one we don't have such uplift. We only have some like 1 meter of subsidence. So for the port, we can just fix the thing with just 1 meter. Is not the big issue, but this situation is totally different. So they say this is more harder to make a plan. But one good idea that I recently learned, that they make use of the uplift things. So this one in this area, I think we didn't pass this road during our field trip, but this one they have uplift and they have also landslide, and they have a plan to pave a new road here. So the road can still continue, but keep it as a memorial, so that okay, when people can say, oh, earthquake can cause like uplift, and this is the remains of the damage caused by 2024 earthquake. So this is one candidates of the memorial facility. And also, yeah, we have the lots of facilities that has been preserved, like this building, but some, or this building as a school, but some others like this ship or this building is already demolition. But these are example from 2004 Indian Ocean tsunami in Thailand and in Indonesia. So still ongoing. What under they have a list of what are possible candidates to be used as a disaster memory facilities. During the field trip, we also have a chance to stop by this post office, where the tsunami reached around, I think, sailing of the first floor. And yeah, from the newspaper, they also mentioned that this is one of the candidate that they will keep it as a memorial facility, so that they can convey or not people not to forget about this kind of this event. So for tsunami part, I would like to also spend another 15 minutes maybe about what after this earthquake, what we have been doing so far for more research detail. Actually, just 2 years before that earthquake, also our earthquake professor asked us like, okay, he's concerned about earthquake and tsunami in this area. Can you do simulation for us like that? Is what he have like a sixth sense maybe. I don't know, but we did that actually, yeah, already there, but we like we did that, but we cannot speak out loud, or we don't have chance, or like we didn't think that it will happen just 1 year after, and it happens. So, and yeah, because it's not only in this area, but you can see tsunami also reached to the other side, to the South Korea side as well, or the Russian side as well, but it's not that damaging thing, but tsunami can be observed. And this is the first major tsunami warning. That means tsunami more than 3 meter record in Japan after 2011 tsunami. After 2011 tsunami, we had tsunami warning after 2016 earthquake in Fukushima here. But this is the first time that they launched the major tsunami warning. So that means they expect tsunami more than 3 meters in this pink or violet zone, which is Noto Peninsula. And for tsunami itself, as I mentioned, this area has uplift, so it was okay for the tsunami. But for other area, like here, tsunami arrived very soon because it's just located in the fault. But people has very awareness. As I mentioned, the government has a new assessment after 2014. So they aim to be able, when they do the drill, they should be able to evacuate within 5 minutes or something like that. So this is the good thing. They didn't have a wrong image of the timing. Because in case of 2011, we had like half an hour or 1 hour before tsunami arrived. But here is the situation different, but they have a good information. And from the CG, for example, in this port, we can see that like the wave from the south and wave from the north somehow combine here and make bigger tsunami and make the inundation to the ports. So this is how also like we use simulation techniques to explain the local situation. And this is the example how the damage looks like. Yeah, it's not that big compared to 2011, but still very damaging. And some area like the breakwater got damaged by the overtop tsunami, and the area here totally destroyed. And recently my colleagues they built also they have the data of damaged building, and they do the survey of flow depths here, and they make fertility curves for building as well caused by tsunami. And when they compare with the fertility curve of tsunami in 2011, we can see that this one of course is much weaker because the building are more is older, and of course they received the damage from the earthquake already before tsunami came. So this is maybe we can do more analysis for detailed things. This time, luckily, it was still, you can see here, just before the sunset. So we still have many chance of, like video camera along the coast of Japan. So this is one example that we take the data from a TV company, and you can see that at the just the time of earthquake, you can see that there are many people. Actually, this is one of the sightseeing area. So Susanna and Joanna, you can see what we see last week is much more beautiful, right? blue sky, and this one, but this one is quite cloudy. But anyway, so they can see that many people, but soon when the camera shake, soon everybody already evacuate. So they have very well, of course we have the warning as well, but they have people, even they are tourists, but they have very high awareness. They could evacuate. So this for us as in our tsunami community, we say this is one of the good example of successful things. Of course, still two people die by tsunami, but compared to such situation like this, but most of people can evacuate. So for us, everybody in our community say like this is a good example, although the size is quite limited, but yeah, still. And but in terms of warning, actually there are some issue that we have to, not we, but I mean the JMA, the Japan Meteorological Agency, that realize, and they are going to improve, which is the warning criteria. So of course the epicenter was in here in the peninsula. So if you have a look at this here, sorry, it may be small, but the violet, the purple area here in the peninsula is where they say, okay, major tsunami warning. So they expect tsunami more than 3 meters in this area, which is okay. So from our field survey, we also found that the tsunami trace height go up to 5 meters. This makes sense and correlated to the warning. This area, this is inside the bay, as you can see from this animation, is quite far, and the tsunami itself was weak, less than 3 meters. And the government, the official warning said also tsunami warning, which is between 1 to 3 meters, and the actual height is about 1 to 3 meters, which is also fine. This is follow the categories of the government. But the problem is this one. The official warning only say tsunami warning, which is they expect to be 1 to 3 meters, but the actual tsunami was like 4 meters. So they underestimate. And the reason is that why my computer? Maybe I will come back here. So actually the fault line, of course, because epicenter was here, So when JMA use the database, they are mainly based on the epicenter of the fault. But when we try to, you know, like simulate the tsunami, that so that we can fit the height of tsunami all along this area, we finally found that actually the fault line is actually extend more east. Some people even propose around here. So that's why the tsunami from this part of the fault go directly to this area. That's why tsunami here is much bigger than what the official warning estimates. So of course now JMA realized this problem. So I'm sure now they have already improved or add more case or something like that. But this is what we also noticed after the event as well. Another thing is that the here this is the waveform, which is the water elevation that record for along several stations. And see, you can see like Sado or Kashiwazaki, it's far from the source, right? So we can see the tsunami signal after a while. But in Toyama, very soon after earthquake, the red dashed line, you can see the wave, the minus wave, negative wave already arrived. So it's impossible for earthquake generated tsunami to make these things very soon after the earthquake. So we suspect the other reason, so which is the submarine landslide. And actually we have similar evidence in 2007 earthquake, where again they found that if they simulate tsunami just from this fault, the wave has to go through indirectly like this to here, which takes a long time. But they could observe tsunami very soon after earthquake. So they say in this paper that because of the ground shaking here, it generates small submarine landslide here, and that's why tsunami could be observed here very quickly. And actually, my another colleague, they already publish make some research, and this is also again before before the earthquake. They say the possibility of submarine landslide along this side of Japan, but of course we need more research to do more assessment. But yeah, the thing just happened before we study in detail. And Japan Coast Guard, they do the bathymetric survey after the tsunami, and they have a good bathymetry data before the tsunami as well. So they compare the data before and after, and they can see the blue lines are the cross section of the sea floor before earthquake, and the red one is the after earthquake. And they can see, they suspect several area of submarine landslide. So this the gap of the topography bathymetry. So this part might be slide like that. And from our preliminary study, we also test like, okay, the black line is the tsunami on the observation data. And if we only simulate tsunami from earthquake only, it's a blue line. There is nothing here. We cannot explain this part of the wave. And if we try, okay, let's try just one landslide here, we can see that, yeah, they can make something here. Tsunami from landslide. So we are working with geotechnical engineering professor in Irides. We use more like soil conditions, soil data, and we calculate the slope failure. And then we consider more like geotechnical parameters, and we can somehow guess the location of landslide and also the depth of the landslide. And so we say, okay, if the safety factor is less than 1, it's most likely that that area will be slide. So we use the location and the depth of the landslide as an initial input for our tsunami simulation. So we couple the landslide model and our traditional tsunami model for this simulation like this. And just in brief, so we can somehow because from tsunami from here, from the source to Toyama, it took about 20 minutes. So this part is actually tsunami from the earthquake, and this part is tsunami from landslide. And from our this initial result, we can somehow reproduce the tsunami, both amplitude, negative amplitude, and positive amplitude, and also the wave period as well. So this is how we can also explain the very complex situation. And yeah, we also actually we applied the same thing for Palu tsunami as well, and we did more case so that we can establish a new way of doing things. And just for future, I just have three more slides just to let you know like what is the perspective of the future of big earthquake and tsunami. Sorry, this is an old figure, but just to give you some an idea that the government has already like do some assessment of earthquake for a long time, and which area, what is the probability like that. And what they worried is the Nankai Trough, which is in this area of Japan. Why? Because there has the long history of the earthquake since more than 1,000 years ago, and it has three blocks: Tokai, Tonankai, and Nankai. And sometimes they just happen separately, but some like in 1707 three blocks breaks altogether. And what they're worried because the last one in Tokai was in 1854, and in 1946 the Tonankai and Nankai already rupture, but Tokai one is already more than 170 years. And if you make a rough calculation, you can see that it's about 100 years or 150 years. So it's like it's already about the time of this one. So that's why they are quite worried of this one even before 2011 tsunami. And last year in August there was so I mean sorry, so because of this they already marked the red zone. Okay, if there is any magnitude 7 or bigger earthquake in the red zone, they will release the possibility of Nankai Trough earthquake. This is how the system worked. And last August there was a magnitude 7 just around the edge of the red zone, and the government has to make this kind of warning. But unlucky that it was during like long holiday in Japan, and people already like booked train ticket, book the hotels, things like that. And the government also difficult to say very clear that what they should do, what the people should do like that. So yeah, I think it's quite painful for in terms of economic loss after that, and that it remained for a week. And actually this year in January, again, another earthquake happens around here, but at that time in January, the magnitude is slightly lower than 7. So they didn't make another 1 week of warning. But yeah, so I think now the government is still under the consideration if they will continue this kind of system or how they can improve. So this is just to show like after earthquake, more than around 7 magnitude happen within half an hour, they will consider okay if they will release this kind of warning or not, etc. So and yeah, even though in the past this is the same data as this one, but just in terms of the map. So you can see that even though the history earthquake in Nankai Trough, the rupture area is only up to here, not reached to the epicenter. But I think the government just want to make sure that they have enough more conservative. So that's why they increase the area up to here, and that's why it reached to the epicenter of the last August things. And actually, this idea is not only for Nankai Trough, but in Toku region also we have the same thing. That this is the rupture zone of 2011, and if you remember, actually at that time, just 2 days before, on March 9, there was a magnitude 7.3, and there was I think tsunami warning or advisory, I forgot, but yeah, there was a kind of warning, but no big tsunami observed. So it's quite tricky, like, so on this day there was like warning or advisory of tsunami, but nothing much happened. So, and then just after 2 days of a warning again, but very big one. So it's like a foreshock and aftershock like that. So same thing to Nankai Trough in Tohoku region. We also have this kind of system. So in the future, in this red zone, if there is any magnitude of 7 or more happen in this area, the government will do the same thing to do this kind of possibility of major earthquake, etc., like that. So that is what is going on. So the area that we are concerned. And in Japan, there are many, not only like trench here or trench in Nankai Trough, but also many active faults in the country. And 2024, the Noto Peninsula earthquake also one of these, like many active fault in the country. So still, yeah, we have to also have our eyes on. This is my last slide. I would like to also make you draw your attention that based on our collaboration, this I would like to also thanks to Tizana and her team and Keith also here, that finally, yeah, our long collaboration, we somehow reward by a very nice, very high level yeah, award. So I would like to use this chance to even though my background, my specialized tsunami, but thanks to you guys and also with Susanna and Jonah, we have chance to explore more new topic on liquefaction on this Noto Peninsula grant by another funding. So hopefully by listening to my talk today, you can see that there are several things to do related to 2024 Noto Peninsula earthquakes, not only earthquakes, tsunami, but other things that can be worked together. So I would like to seek for this opportunity to work with other UCL members as well. And yeah, thank you for your attention. This is a nice photo that we found the field trip. You can see the watermark, and like we saw this cat. Hey, is this alive? We will go closer, and he or she tried to show like stand up, and this is just the same height as the height of the cat. So it's very lovely to see. Well, anyway, thank you so much for your attention. So if you have any question, I also have our colleagues from Tokyo University as well. Maybe we can have some discussion. Thank you.
Thank you. If those online would like to ask a question, if they can maybe put their hands up or write it in the chat.
Oh, shut. Maybe then I stop my screen. I can see. Oh, it's not in the chat. It's the Q&A. Then what should I press? I press this one? No, I think we just speak out maybe. But I think online people cannot see this, right? Maybe I should.
They can see they can see you.
Oh, really?
Yeah, they see you. They
But
don't see the chat.
yeah, they cannot see this question, right?
You can share again, but it is in the chat.
Yeah, this Q&A. So the question is, can geometry of the coastline play a role in tsunami height, in particular place such as complexity and cavity? Yes. So yeah, to answer, yes. So tsunami height is really varies to the local topography. You can imagine a good easy example is like if we have the V-shaped coastal line where tsunami can be shape and amplify. So this is another example. Or if we have a bay where tsunami can easily split out, or some area like the one that I show in animation, we call edge wave, where we have like the curve, and tsunami can just go propagate through along the coast like that. So yeah, so to answer your question, yes, so the local geometry is very important. So unlike earthquake intensity, maybe more simple. I mean, sorry to say that, but I feel like, I mean, maybe you model soil condition and things like that. But yeah, for tsunami, we really have to consider about the local topography. Yeah, sure.
So one of the things that came through out of your presentation was that you're expecting where there are gaps in the faults, you're expecting them to rupture next. So it's sort of this idea of a seismic gap theory. Does that actually feed into the probability assessment of a tsunami taking place?
Yes, yes.
You might repeat the question.
Yeah. So the the question is like if the government or they consider the seismic gap into the probability of the earthquake. Yes, the answer is yes. So if you remember, I showed one slide about the maps and location of the fault and probability. Yes, that has been updated for, I don't know how frequent, every month maybe. So
Okay.
they consider like that. Yeah. But after not the earthquake, they what we learned from local university, they set up the committee again to study the new possibility. They have, of course, they think about the gap, and also they think of like if we have one fault line. Until now, they only think the possibility of this earthquake happen separately.
Yeah.
But now whatever is okay. They think about worst case, so they connect two in one to make it more bigger like that.
And how does that affect? Because one of the things that we showed on the slide was with the seismic gaps, you showed an assumed epicenter for the earthquake.
Mhm.
But actually, what happens if the epicenter isn't there? What happens if it's something different? Because what you said about the Noto Peninsula was that the idea was that the epicenter was more to the north.
Yeah. Yes.
Than it was assumed in the past. And that obviously has a profound effect on arrival times.
Yeah. So the question is about the how to say this discrepancy between the epicenter as a point
Yeah.
at the real situation of the fault as a area.
As an area.
Yeah. So that's always the problem, and that's not, it's not reflect also the orientation of the fault as well. Yeah, you are right. So like if you think about tsunami, so if the earthquake, yeah, if the epicenter is here, then I should show this one. Yeah, actually, like maybe I would say like this, the fault rupture, like 50% of the energy is actually inland, so it's not convert to tsunami. So that is another problem of why we underestimate the tsunami. And also, not this case, but in 2016 in Fukushima, and maybe I can show which one is better. Sorry, it's quite small, but like in this bay, like we call Sendai Bay, where like in JMA database, they only have two types of fault orientation, which is like 0 degree or 90 degree. But actually the fault is like 45 degree, which is like this. So the energy can be easily go through to Sendai, but from 0 degree or 90 degrees it's not, so they underestimate. So again, only as a point cannot fully explain the situation. Yeah.
Thank you.
Thank you.
Are there any more questions?
One question for me.
Yeah.
Can you go back to the fire? What started the fire again?
Which
And
one?
The fire that
Oh.
followed the earthquake.
The location?
is there any lessons learned from that to prevent it in future earthquakes? Because it was a complicated situation. So
Yeah. For me, I don't have a good answer right now, but I mean, what I would like to say is that people keep saying what will be the, how to say, fighting guideline or regulation for under tsunami warning situation.
Okay.
I think still no new guideline or new things for that, but yeah, now we realize that okay, during tsunami, fire can happen and we have to stop the fire. But yeah, well, that is yeah.
What started the fire?
From my read in the newspaper, they said the building might destroy the electricity line or something like that, and it sparks and then it fire. And sorry, and this is the how the fire spread from this point. Follow the arrows. Even though it's very near to the river, but as I mentioned, the firefighter has to evacuate and the uplift, so they make more difficult to pump the water from the river. Yeah, again, yeah. I think uplift also another things that they never considered. Yes, Susanna.
You said that there isn't a lot of damage related to the whole event, but the event had lots of possible triggers, I mean, or possible reasons for the failure. For example, I remember this place with the manhole, there's clearly liquefaction on top of the tsunami.
Yeah.
Or the fire, there is the fire, but the fire is caused by the earthquake. What is the cause that you record as the main one for the failure, for the damage?
Earthquake, ground shaking.
Yeah, but this is not probably not that, no?
Yeah.
Or is the fire, or is?
Yeah.
Did you exclude the ones that were clearly something else, like the buildings bent or the, I don't know, landslides that probably created some damage?
Yeah, it's quite, I mean, only for the area that only have earthquake and we see the building collapse, that may be easy, but for other like liquefaction of fire is it's mixed up everything, so it's difficult to say how. But on the other hand, I think it's a good chance, like for tsunami, for example, like I show here with like, yeah, for tsunami, like this building was already or other area, they already received earthquake before tsunami arrived. So we already have tsunami fragility for this area, so we can compare with previous one like 2011 where the building is strong, so we can see how more quantitatively how combined impacts can create more damage, yeah, quantitatively. So yeah, that is a good night for research. About the time.
Sorry, I'm going to speak from here so that
Okay.
you don't hear the resounding noises. But yes, we're coming to the end of the talk. So I would like to thank Professor Anwar Tupazri for his talk and for answering the questions. And there are
Thank
many.
you.
This is a fascinating earthquake event. Well, not just earthquake event. And thank you again for taking the time to speak with us.
Yeah.
Please join me in thanking.
Thank you so much.
Thank you to all those online for participating.